Whether am I audible? Am I audible now? Whether am I audible? Yes, I think I am audible. So without any further delay, let's just start our class. So today we are basically going to, yes, thank you. So today we are going to discuss about harmonic oscillator problem. This harmonic oscillator problem plays an important role in your CSIR-NET quantum mechanics portion. Every time you get a question from harmonic oscillator problem, so it is very necessary to understand this harmonic oscillator problem. Now, before you start, let me just tell you guys, my name is Sahin Sorifi and I am a class educator on Unacademy, and these are some courses which are currently ongoing. This is a batch course where we are covering the whole syllabus of CSIR-NET 2020 June exam, and other than that, a complete course on thermal and statistical physics are also going on, and detailed course of electromagnetic theory is starting from this Monday. So you can join it if you want to cover the whole electromagnetic theory in detail. And this another batch number 4 is going to start from February 22, and this will be taken by 5 educators. Okay. So if you want to join these groups, join using our referral code physics hub or SahinLive. And guys, this is our class schedule, so you can just take a note on it. Every Thursday, Friday and Saturday we are taking free classes, and Monday to Saturday 9 to 10:30 p.m. we are taking Unacademy plus classes. Iconic subscription you can take, you get a lot of benefits. Other than the plus benefits, you get also some additional benefits: SOP interview preparation, preparatory study material, personalized doubt clearing, study booster session, weekly reviews, and many more things. So think of taking an iconic subscription as well. Use our referral code SahinLive to get 10% off. Now let us just start our class. So we'll start with the basic one-dimensional linear harmonic oscillator. We'll start with basic one-dimensional linear harmonic oscillator. So in your class 12, I think you have studied about this one-dimensional harmonic oscillator. So how do we define a harmonic oscillator? When we call something that it is moving in a harmonic oscillatory motion. Okay, so you must have seen this example of pendulum. Okay, so if you have a pendulum, so it keeps on oscillating about some mean position. Okay, so this is your mean position with respect to which this bob keeps on oscillating on this side and on this side. Okay, so what is the definition? So this can be regarded as one system. So if a system, कोई भी system अगर vibrate करे about an equilibrium position, such that, what should be the restriction imposed on it? Such that the magnitude of force acting on it is proportional to the displacement. Proportional to the displacement from the equilibrium position. Okay, so let me just tell you our brief idea about the class. Here today what we are going to do, briefly I will tell you about the classical oscillator. Okay, then we'll try to correlate that to quantum harmonic oscillator. Okay, that is why I have started with classical one, because you already know that, and it will be very beneficial that if you can revise this classical portion, then you can easily relate it to quantum. What is the difference between them? So what is a harmonic motion? So you see the magnitude of the force acting on it proportional to the displacement from the equilibrium position. If this is the equilibrium position, if the particle is here, it will experience some force in the negative direction. Okay, and if the particle comes to this position, it will feel larger amount of force because the displacement from the equilibrium position is more here. Okay, so that is why the magnitude of force acting on it is proportional to the displacement from the equilibrium position. Now the next one is the direction. Okay, what is the direction? The direction of the force, direction of force is opposite to the displacement. You are giving displacement to this direction, so it will be opposite to the displacement, and this is known as LHO. If a system exhibits this property, this is known as linear harmonic oscillator. Linear harmonic oscillator. So what are the examples? One example I have already shown you. This is a pendulum, simple pendulum. This is one example of linear harmonic oscillator. Other than that, what can be the possible examples? Spring mass system or spring block system. Any floating body, like if you have some water, okay, and if you have some lighter body, and if you want to immerse it into it, then what will happen? If you apply some force here in the downward direction, it will keep on oscillating. This body will keep on oscillating. If it floats on that particular liquid, then also it will show this harmonic motion. Okay, so this is the basic idea of linear harmonic oscillator. Now let's talk about classical harmonic oscillator, classical linear harmonic oscillator. Okay, classical linear harmonic oscillator. What do you know in case of a classical linear harmonic oscillator? So let's say we have a mass m. This mass is constrained to move in the x direction. Okay, let at any time t, at any time t, the displacement from this is, let's say, x. Okay, at any time t, the displacement of the mass m constrained to move along x axis, constrained to move along x axis is x. Then what will be the restoring force acting on it? Let's say we have this spring mass system, okay, like this. So if this is showing some displacement along this x direction, so some restoring force will be acting in the opposite direction, restoring force. Okay, so how can we express that restoring force? What is the restoring force on the particle? So your restoring force on the particle will be F equals to, F is proportional to x, so F equals to minus kx. This is Hooke's law. K is the constant, which is known as spring constant. Okay, now what is F? From Newton's laws of motion, you can write F as d square x by dt square. This is equals to minus kx, m into d square x dt square. Therefore, we can write d square x by dt square, and you can take it on this side. So plus k by m into x equals to 0. We write this equation in this way: d square x by dt square plus omega square x equals to 0. Okay, where omega equals to root over k by m. So this is the equation of an harmonic oscillator: d square x by dt square plus omega square x equals to 0. Let's say this is equation number 1. So this differential equation is followed by oscillator. Now what is the solution of this particular differential equation? You must be knowing about its solution. What is the solution of this particular differential equation? So we have this differential equation: d square x by dt square plus omega square x, this is equals to 0. What is the solution? The solution of this differential equation is given by x equals to A sine omega t plus phi. Okay, what does this represent? This is the representation of simple harmonic motion. Simple harmonic motion, in short SHM, of the particle with frequency. What is the frequency? Frequency is given by nu. Nu equals to omega upon 2 pi. So 1 by 2 pi root over omega equals to, we have got k by m, root over k by m. So this is an equation representing simple harmonic motion of the particle with frequency nu equals to 1 by 2 pi root over k by m. Now, what will be the potential energy? Potential energy of the particle. Potential energy of the particle. Look, the mass was attached to some spring. Now it is showing some displacement in this direction. So it will definitely restore some kinetic energy and potential energy as well. What will be the potential energy? EP. This is equals to half k x square. And k equals to m omega square. So this is equals to half m omega square x square. And what about kinetic energy? Kinetic energy of the particle will be Ek, half mv square. This will be equals to half m omega square a square minus x square. So this will be the expression of potential and kinetic energy. Now what will be the total energy? From these two expressions we can find out the total energy. So guys, before going to the quantum harmonic oscillator, we are just revisiting our classical oscillator. So this will be half m omega square a square. This is a constant. Okay, so you can see the total energy of the particle exhibiting simple harmonic motion is constant. So this is a linear harmonic oscillator in classical regime. This is a linear harmonic oscillator classical regime. I hope this is clear to everyone. Is there any question? If there is no question, we can move forward to quantum harmonic oscillator. Quantum analysis of linear harmonic oscillator. Is there any question, guys? You can let me know in the comment section if you have any question. Otherwise, we can go for quantum analysis of linear harmonic oscillator. So let's go to quantum analysis of linear harmonic oscillator. So what are the changes which we can observe in linear harmonic oscillator in case of quantum mechanical case? So if we have a particle which is kept in some potential, harmonic oscillator potential. Okay, so we have a particle of mass m. Okay, and it is moving in the potential, harmonic oscillator potential, in the potential in the form, let's say v of x equals to half k x square. What is this? This is equals to half m omega square x square. What is the form of this potential? So basically the particle is moving in this harmonic oscillator potential, half kx square. Okay, so if this is v of x, this is x, so this is your half m omega square x square or half kx square potential. So here we are going to utilize our quantum mechanical approach. So in quantum mechanical approach, what we utilize Schrodinger equation. In classical we applied, you see here in classical mechanics we applied Newton's law. Okay, here we applied Newton's law. This is your Newton's law. But in quantum oscillator, we are not going to utilize this Newton's law. Rather, we are going to utilize Schrodinger equation. Okay. So before we apply Schrodinger equation, we need to know about the Hamiltonian. So what is the Hamiltonian? Hamiltonian of the system. How do we write Hamiltonian? Hamiltonian को कैसे लिखते हैं? Hamiltonian is basically kinetic energy plus potential energy. What is kinetic energy operator? Here you have to think everything in terms of operator. So how kinetic energy operator is minus h cot square by 2m d square by dx square. Okay, this is the kinetic energy plus the potential energy we have already know, half m omega square x square. So we got the Hamiltonian of the system which is moving, or Hamiltonian of the particle of mass m which is moving in the potential v of x equals to half kx square. And what is this? This is your one dimensional linear harmonic oscillator potential, LHO, linear harmonic oscillator potential. Okay. Now once we get this Hamiltonian, we can write the time independent Schrodinger equation. Time independent Schrodinger equation. Okay. So how can we write the time independent Schrodinger equation? Minus h cot square by 2m d square by dx square plus half m omega square x square. H psi equals to U psi. The formula is H psi into U psi. This is H into psi. H psi equals to E into psi. Okay. So if you rewrite this expression, we can write it in this way: d square psi by dx square plus, we can write twice m by h cot square into E minus half m omega square x square into psi. This is equals to 0. So this is the differential equation followed by a particle which is moving in a harmonic oscillator potential, one dimensional linear harmonic oscillator potential. Okay. So in classical case, we got this expression. In classical case, we got this expression: d square x by dt square plus omega square x equals to 0, and the solution was given by this. And in quantum case, what we are getting? In quantum case, we are getting this equation. Now this equation is also a second order differential equation. We need to solve this. Okay. So if we solve this particular differential equation, what will be the solution? The solution of this particular differential equation will be, so solving the equation, let's say we are naming it as equation number 1. So solving equation number 1, what will you get? Solving equation number 1, we get the normalized wave function. Normalized wave function of linear harmonic oscillator. This is very important, guys. This wave function form needs to be remembered. Linear harmonic oscillator in the nth state. इसको आपको याद रखना पड़ेगा. The expression is given by psi n of x. This is equals to alpha by 2 to the power n into n factorial root over pi. Little bit complicated expression, to the power half e to the power minus alpha square x square by 2 h n of alpha x. Okay, where this alpha square equals to m omega by h cot, or alpha equals to root over m omega by h cot. You need to remember this. Actually, in your question, different states are asked. Like if it is ground state, it will be psi 0x. If it is a fast excited state, it will be psi 0x, psi 1x. Second excited state, psi 2x, and all. Okay, so let me just write for you some of the wave functions. So ground state will correspond to n equals to 0. Okay, the relevant wave function is psi 0 of x. तो पहला एक दो याद रख लो, मतलब just try to remember psi 0x, psi 1x, then that will be enough. So psi 0x will be how much? If you put n equals to 0 here, you see this will give you alpha by root over pi to the power half. Okay, e to the power minus alpha square x square divided by 2. Hn alpha x h0 means 1. So that is why this is the ground state. Okay, now if you plot this ground state, psi 0 of x alpha by root over pi to the power half e to the power minus alpha square x square by 2. If you plot this, you will get a wave function like this. So you see, exponential term is that this is a Gaussian form. That is why you are getting a Gaussian wave function. So this is the ground state of a linear harmonic oscillator in quantum region. Linear harmonic oscillator, linear harmonic quantum oscillator. This is the ground state wave function form. Okay, and you can see from this expression psi n of x, you see e to the power minus alpha square x square by 2 hn alpha x. So these two terms are there. So it has a special property, guys. What is that special property? The special property is, here you just keep it as note 1, psi n of x, it is even for even n and odd for odd values of n. And number two is psi n of x has n number of nodes. Now what is node? Node means where the wave function is becoming 0. So in psi n of x has n number of nodes. For psi 0 of x, n equals to 0. So there is no node. That is why you see the wave function is not becoming 0 anywhere. So that is the meaning of this. It has no nodes. So ground state has no nodes. Means the ground state wave function is not becoming 0 at any point of x. Okay. So by putting n equals to 0, we are getting ground state. Now what will you do for getting fast excited state? So for n equals to 1, we get fast excited state. Okay, so what will be the fast excited state? We just put the value n equals to 1 in this expression. So alpha by 2 into 1 factorial into root pi. So alpha by 2 root pi to the power half. Okay, alpha by 2 root over pi to the power half into e to the power minus alpha square x square by 2 will remain. Hn alpha x. What is the value of h1 alpha x? H1 alpha x is equals to how much? 2 alpha x. Okay, so this is for the fast excited state. And if you draw it, so as you can see, wave function has n number of nodes. So here n equals to 1. Okay, so how many nodes it will have? It will have 1 node. The form of this wave function will be like this. So you can see this is psi 1x basically. So this function is becoming 0 at this point. So it means it has 1 node. Clear? Let's say n equals to 2. N equals to 2 will give you second excited state. Second excited state. So psi 2 of x, it can be written like this. Similar way, if you put the value of n to be 2 to the power 2 square into 2 for 8 ho gaya. Okay. So alpha by 8 root over pi to the power half. Okay. E to the power minus alpha square x square by 2 into 4x square alpha square minus 2. So this is the second excited state. And you see for n equals to 2, it will have 2 nodes. Okay, it should have 2 nodes. So what will be the form? What will be the form or representation of this wave function? We can draw it in this way. Okay, so it has 2 nodes, means it will be 0 2 times. That's the meaning, and the form will be looking like this. Okay, so you can see it is becoming 0 at this point and at this point. So it has 2 nodes. Wave function is vanishing 2 times. I hope this is clear to everyone. So solving this differential equation, we got the energy eigen function. This is basically energy eigen function. Now what is the energy eigenvalue of quantum harmonic oscillator? So that's what we need to discuss now. Energy eigenvalue. Energy eigenvalue of a particle moving under linear harmonic oscillator. That will be En equals to n plus half h cut omega, where your n runs from 0, 1, 2, 3. So if you choose n equals to 0, you get half h cut omega. Okay, so you see this is an infinite sequence. N can take any value from 0 to 1, 2, 3 up to infinity. So this is an infinite sequence of discrete energy levels. Okay, with equal energy interval of h cut omega. This is n equals to 0, this is n equals to 1, n equals to 2, n equals to 3, and so on. They are equally spaced and they are discrete. Okay, so these are basically your discrete energy levels with equal spacing. Okay, so basically this sequence is an infinite sequence of discrete energy levels with equal spacing of h cut omega. Now when n equals to 0, for n equals to 0, we get E0 equals to half h cut omega. This is known as 0 point energy of the harmonic oscillator. 0 point. Is it paused, guys? Is it clear or is it paused? Pause हो गया क्या? So if you represent this in this way, let's say this is energy and this is x and this is the harmonic oscillator. Okay, so the energy levels will be equispaced like this. This is your ground state, GS. This is your first excited state. This is second excited state. This is third excited state. This is fourth excited state. And the energies will be E0. E0 equals to half h cut omega. E1 3 by 2 h cut omega. E2 5 by 2 h cut omega. E3 7 by 2 h cut omega. E4 9 by 2 h cut omega. Okay, now I have told you that it has 0 point energy of half h cut omega. Now can we prove that? Can we prove it numerically, existence of 0 point energy according to uncertainty principle? So this is basically this is a proof of existence of 0-point energy according to uncertainty principle. So you can use uncertainty principle and you can show that 0-point energy exists. 0-point energy means it should have been 0 actually, but for in case of harmonic oscillator we are getting it half h cut omega. Why it is so? We can prove it by using uncertainty principle. Okay, so as we discussed earlier that we have a particle m which is executing simple harmonic motion, executes simple harmonic motion along x-axis. Okay, now at time t the displacement is x, so at time t its position is x from the mean position. Okay, so we have considered a particle which is moving in this harmonic oscillator potential and its position is x from the mean position at some time t. Okay, now what is the total energy? Total energy of this harmonic oscillator is linear harmonic oscillator E equals to Ek plus Ep, sum of kinetic energy and potential energy. What is the kinetic energy? Kinetic energy is given by P square upon 2m. What is the potential energy? This is the potential energy of this curve is half m omega square x square. So half m omega square x square. Fine. We can write P square as uncertainty in P, delta P square divided by 2m plus half m omega square delta x. Clear? So this is the total energy. Now you see delta x, this is equals to x. Then what will be delta p? Delta p will be equals to, from uncertainty principle, what you can write? H cut by 2 into 1 by delta x, because delta px equals to h cut by 2 from uncertainty principle. So delta p becomes h cut by 2 delta x. Okay, so we can write h cut by 2x. So what will be the total energy? Your total energy E becomes P square by 2m, so 1 by 2m. P we have got h cut by 2x. So we'll just put the value of P here. So 1 by 2m into h cut by 2x whole square. P square by 2m plus half m omega square x square. What it will produce? H cut square by 4 into 2 8 m x square plus half m omega square x square. Now for 0-point energy, what is the condition? Or 0-point energy. For 0-point energy, dE upon dx would be 0. Okay. So d upon dx equals to 0 means minus h cut square divided by 4m x cube, derivative of this thing, plus half to cut gaya. It will be m omega square x. This is equals to 0. Okay, and from here we can see this x square, so h cut square divided by 4m x cube, this is equals to m omega square x. Okay, so x to the power 4 हो जाएगा, तो x square equals to h cut by twice m omega. Can you write it? X square, value of x square to be h cut by twice m omega. Can you write it? this value needs to be recorded. So this for 0 point energy, x should be in this way. So if you put this value of x in the energy, its expression itself, you get the minimum energy. So therefore, the minimum energy of the oscillator, minimum energy of the oscillator becomes E minimum. E minimum becomes, you see here, h cut square by 8m x square is there. We will just put the value of x square. So h cut square by 8m we are keeping as it is. 1 by x square is twice m omega by h cut. Okay, twice m omega by h cut plus half m omega square x square plus half m omega square x square is h cut by twice m omega. Right? What it is producing? 2m 4m हो गया, 4 हो गया, h cut, so 1 by 4 h cut omega plus यहाँ पे क्या आ रहा है, mm कट गया, omega कट गया, so 1 by 4 h cut omega. So this is giving you half h cut omega. So getting it now? This is the 0 point energy. So you can utilize Heisenberg uncertainty principle to confirm that 0 point energy exists in case of harmonic oscillator. Okay, and that is the significance. So this proof is very important, guys. In your interview also they can ask you this type of question, that what do you mean by the 0 point energy of harmonic oscillator. Then you can explain this using uncertainty principle, that we get the minimum energy of a harmonic oscillator to be half h cut omega. I hope this is clear and you found it interesting. I hope I found it interesting, because using uncertainty principle you can easily prove it. Is it done, guys? आगे बढ़े. Now we have described the theory portion a little bit. Now let's try to solve some problem. Problem करें. Problem कहाँ गया? Yes, this is the first problem. The energy levels of a particle of mass m in a potential of the form v of x equals to infinity when x less or equals to 0 and half m omega square x square when x is greater than 0 are given in terms of quantum numbers n equals to 0, 1, 2, 3. Then what will be the energy level? Okay, Leon, just try to do this. Leon Mustaq. So what is the situation given to us? Till now we are discussing this harmonic oscillator. Okay, so the whole oscillator was given, but here you see it's a half harmonic oscillator. This is v of x, this is x. So x less or equals to 0, it is infinity. Okay, so this is like this, it cannot go in this side, but in x greater than 0 it is half m omega square x square. So this is a half m omega square x square in this region where the potential due that wave function psi n of x, this is even for even n and odd for odd n. Here at x equals to 0 the potential is infinite. Okay, at x equals to 0 vx equals to infinite. What does it mean? The wave function must be 0. The wave function vanishes at x equals to 0. Fine. Now what is the wave function of harmonic oscillator? Psi n of x, this is equals to a, let's say constant we are taking a, e to the power minus alpha square x square by 2 hn alpha x. Now we have to check the wave function at x equals to 0, and those wave functions which will be 0, though only those are allowed. Okay, so at x equals to 0, which one of the wave functions are getting vanished? those will be allowed. Okay, so you see where I have told you that. Look, let's take the example of the first excited state n equals to 1. If you put x equals to 0, this is 0. So this is in accordance with the condition that psi n of x is 0 at x equals to 0. But here for n equals to 2, even you see if you put x equals to 0, this is not 0 because another term is there. So this is psi 2 of x is not 0 for x equals to 0. Similar way, you will find that psi 3 of x is 0 at x equals to 0, but psi 4 of x is not equals to 0 at x equals to 0. What does it mean? What does it mean? It means psi n of x equals to 0 for n equals to 1, 3, 5, 7 means odd values, and psi n of x, ये मेरे पीछे हो गया, sorry, psi n of x is not equals to 0 for n equals to 2, 4, 6, 8 means for even values. Okay, so these even values are not allowed. So allowed n values are n equals to 1, 3, 5. Okay, now here you have to express this n in terms of 0, 1, 2, 3. So energy expression was En equals to n plus half h cut omega, but only you see what values are allowed. So in place of n, we have to write 2n plus 1, that is making n to be what? So 2n plus 1 plus half h cut omega, because only odd values are allowed. So this is equals to 2n plus 3 by 2 h cut omega, where n equals to 0, 1, 2, 3. So there are two ways to write this result. One, either you express this in this way, En equals to 2n plus 3 by 2 h cut omega, n will run from 0, 1, 2, 3 dot dot dot, or you can write En equals to n plus half h cut omega, but here you have to specify that the allowed values of n are 1, 3, 5, 7 dot. So these two things are correct, only you have to specify the n. If you are specifying n at 0, 1, 2, 3 dot dot dot, it will be 2n plus 3 by 2, or if you are specifying it at n equals to 1, 3, 5, then it will be n plus half h cut omega. Now in the question it is given n equals to 0, 1, 2, 3, that is why option C will be the correct option. I hope this is clear. Let's quickly move forward to the next question. Okay, this one question you do. A particle of mass m is confined in the potential. This is also half harmonic oscillator. Same. Let the wave function of the particle be given by psi of x equals to minus 1 by root 5 psi 0, 2 by root 5 psi 1. Psi 0 psi eigenfunctions of the ground state and the fast excited state respectively. What will be the expectation value of the energy? इसका आंसर क्या होगा? What will be the answer, guys? Expectation value of energy is basically E0 P0 plus E1 P1, because only ground state and fast excited state are given. So expectation energy value is basically E0 P0 plus E1 P1. इसका क्या आंसर होगा? Anyone? What should be the answer of this question? Yes, waiting. Take your time. After solving, just comment down the options. Are you getting the answer? What is E0? E0 is the ground state energy. And what is the energy expression? Energy expression of harmonic oscillator is En equals to, we have seen that 2n plus 3 by 2 h cut omega. N runs from 0, 1, 2, 3. So your E0 is basically 3 by 2 h cut omega. Okay. And E1, fast excited state energy, is equals to 2 plus 3 by 2, 7 by 2 h cut omega. Okay. So E0 is 3 by 2 h cut omega. What is P0? P0 का probability of this coefficient square. So minus 1 by root 5 whole square plus E1 P1. E1 equals to 7 by 2 h cut omega. P1 is the probability of this. So root 2 by root 5 whole square. That is enough, no? What are you getting? So 3 by 2 h cut omega plus 1 by 5. So 3 by 10 h cut omega plus 4 and 2. 28 by 10 h cut omega. So 31 by 10 h cut omega. Option A. Okay. I hope this is clear to everyone. Next, so we have till now consider conventional method. Now we are going to take up operator formalism. Okay. So operator formalism of harmonic oscillator. So we'll take up the operator approach to solve the harmonic oscillator problem. So first of all, what you can do, we can express the Hamiltonian of the system. Hamiltonian of the system. So we are writing Hamiltonian in terms of operator. Hamiltonian operator equals to P square by 2m. Okay. So you have to express in operator. So operator sign is this, plus half m omega square x square. Okay. Now we are defining two-dimensionless operator. So we are defining two-dimensionless operator. Dimensionless operators. How the operators are defined? We are defining capital P operator. This is equals to small p operator divided by root over m h cut omega. Okay, this is one operator, and another operator for position x operator. This is small x into root over m omega by h cut. So we have defined these two operators. Then what will be the form of Hamiltonian? Therefore, the Hamiltonian can be written as h equals to, just put p equals to this. So h cut omega by 2, p square is there. So p is capital P square into m h cut omega. So h cut omega by 2 p square divided by m h cut omega. Okay, plus m omega by 2 h cut x square. Can you write it? Look what we have done. Here 2m was there, so we just taken h cut omega in the numerator and we have divided by h cut omega, because we want to express in terms of the bigger p. So we have written this in this way. Here also you can see we have written m omega to h cut small x square. So we can write it like this: h cut omega by 2. This small p square by m h cut omega equals to capital P square. Okay. So capital P square plus m omega by 2 h cut x square. This will be x square. Okay. सॉरी यहाँ पे एक 2 हम लोगों ने ज्यादा ले लिया है ना. So m omega by 2h cut into x square. Okay. Yes, now it is correct. So this is our modified Hamiltonian. I am just writing it again. H equals to h cut omega by 2 p square plus x square. This is our new Hamiltonian. Now what we are doing, we are introducing two non-Hermitian operators. Okay, one is a raising operator, lowering operator. Another one is a dagger. We'll define them about what is this lowering and raising operator. So first of all, a operator is 1 by root 2 x plus ip. These are also known as ladder operator. 1 by root 2 x cap minus I. So these are raising operator and lowering operator. And a and a dagger are Hermitian conjugate to each other. Okay. So if you take a star of it, it will give you back this. Now you can see, if you take a dagger into a, if you take the product, then what it will produce? This will produce half into x square plus p square plus a dagger into a. So I into x dot p, I xp, and minus I px. Okay. So this can be written in this way: half p square plus x square plus I by 2 xp minus px. What is this? The Poisson bracket of x and p. xp minus px. I think it is clear till now. Now can you see this one, half into p square plus x square, it is here in the expression of Hamiltonian. So what we can write? A dagger into a, this is equals to h cut Hamiltonian by h cut omega. Can you write it? What is this? Half p square plus x square equals to h cut by h cut omega, h operator by h cut omega, and xp, so that is I h cut. Okay na? So this is basically minus half. ठीक है. So your Hamiltonian is becoming A dagger A plus half into h cut omega. This A dagger into A, it is known as number operator. This A dagger into A, this is known as number operator defined by n. So n equals to A dagger into A. This is known as number operator. Number operator or occupation number operator. Okay. Therefore, ultimately, we are getting expression h equals to n plus half h cut omega. So in operator formalism also, we are getting similar kind of result. In the last approach, we got n plus half h cut omega. Here also we are getting n plus half h cut omega, where n equals to A dagger into A. This is known as number operator or occupation number operator. Now, let me just give you some of the important commutation relation of involving these number operators, raising operators, lowering operators. So, some important commutation relation. Some important commutation relations. Pehla, A commutation of A dagger. This is equals to 1. Number 2, commutation of number operator and A dagger. This will give you A dagger. You can prove it, you can do it. I'm just leaving it as homework. Okay, number operator, commutation of number operator, and lowering operator is minus of lowering. Hamiltonian. Zero. Okay, this is compatible to Hamiltonian. 5, lowering operator, Hamiltonian. This is equals to h cut omega A. Sujala, what is your height? What do you mean by this? My height. कि मोमेंटम निकालना है मेरे हाइट से अनसर्टेनिटी रिलेशन यूज करके डेल्टा एक्स डेल्टा पी एक्स करोगे फाइव सिक्स. So these are some important commutation relations which may be helpful in your examination. So I think the time is over. I just doing these things. Is there any question till now, guys? And we can discuss after this in some other class. Actually, time is over. So I have to end the class now. And before I go, let me just tell you about few things. So if you have any question, you can just ask me now. So this course is going to start, guys. You can enroll for this course, apply our referral code SahinLive or Physics Hub to get 10% off, and these all courses are also ongoing, so you can enroll for this course. Okay, so thank you very much, guys, for joining this session. I hope you have got some benefit from this class. If you have any question, you can ask me now, or you can also ask it in the group, Physics Hub group. So you can join our Telegram group, Physics, by manually searching this ID, Physics Hub 1. Okay, so thank you very much, guys. Bye bye. Have a great day.